Alrighty, Precalculus CP A4 on Tuesday, May 12th. It's time to get started. Good afternoon. Hopefully you're all having a great day so far. Time to end things off with some pre-calculus. Today, what I would like to do is I'd like to talk about double angle identities as it relates to pre-calculus and all the trig stuff we've been doing. You may have noticed I updated the little sidebar right below me to feature all of the other identities we've been doing. The sum and difference got added, the cofunction stuff. I had to do, it didn't show up on this side. Oh, rats. I did a little Photoshop job to add a minus plus here because that symbol doesn't come in standard and it didn't show up. Oh, rats. I'm going to make sure that shows up here next time. But just like it's written on my page right up here, the minus plus symbol, I tried to do a little Photoshop to make that happen down there. Anyway, hope everybody's having a good day. Today, this is one of the last groups of identities that we're really going to start taking a look at. It's the double angle identities, and it really is an extension of the sum and difference identities that we just talked about. It's essentially taking this and going one step beyond. All right, I'm going to show you what the double angle identities are. I'm also going to run you through a couple examples that involve the double angle identities, and then we'll be all set to go. Just like last week, there is going to be a progress assessment assigned on Thursday. It will be due at 11:59 p.m. on Sunday. I will have your progress assessment that was due this past week. I will have that graded, and I will have the answer key uploaded on Classroom, and I'll have that all taken care of in due time. But it does take a little while to grade it being online, but I'll make sure I get that done as soon as I can, okay? So that can be there for you to refer to. I just want to throw out one more reminder before I get formally started here. Remember that these clips are being uploaded on YouTube. You can go back and watch the lessons at your leisure, and I highly recommend doing so if you ever need a refresher. Just want to make sure everybody is aware that they are, in fact, there and available to watch. That playlist that's linked on Google Classroom gets automatically updated whenever I upload a new one, so just make sure you check that out. All right, in any case, let's get started officially here. Recall from last class that the double angle the sum and difference identities refer to if you have the sign of A plus or minus B, where you're taking two values, adding them together, or taking two values and subtracting them, and then taking the sign of that quantity. The sign of A plus or minus B is the same as the sine of A times the cosine of B, plus or minus, keeping the same sign as whatever's over here, the cosine of A times the sine of B. Likewise, the cosine of A plus or minus B has its own formula. It's the cosine of A times the cosine of B minus plus, which just means that this sign switches. If this is a positive here, it becomes a negative here. The sine of A times the sine of B. Okie doke. What if I now asked you to find the sine of 2A? What if I now asked you to find the sine of 2A? What is the sine of 2A? Well, you could break down something like the sine of 2A and rewrite that as the sine of A plus A, right? Because A plus A is 2A, so he's just breaking down 2A to write it as the sine of A plus A. And the beneficial thing about that is now you could look at something like this and be like, ooh, look, it matches the exact structure as this, the sine of something plus something else. And we could expand it out using this formula. So we could then say the sine of A plus A is the same as the sine of the first thing, that's A, times the cosine of the second thing, which in this case is also A, right? It's the cosine of the second, plus, because the sine's going to stay the same, the cosine of the first thing times the sine of the second thing. Notice what that gives us once we write it all out. We have the sine of A times the cosine of A and another sine of A times the cosine of A. So altogether we have two of those. We could say that the sine of 2A is the same as 2 times sine A times cosine A. And that is, in fact, your double angle identity for sine. I will add that on my little sidebar for next class. You can see there's a little space for it down there. For sine, you can say that the sine of 2A is the same as 2 times the sine of A times the cosine of A, because that just extends directly from your sum and difference identities. Okay? Likewise, we could take a look at the cosine as well. The cosine of 2A. Cosine has a couple different variations associated with it, but we can say, using the formula up here, that the cosine of 2a is the same as the cosine of a plus a, just like before, which means that the cosine of a plus a is then equal to cosine of the first thing, cosine of the second thing, cosine a, cosine a. The sign's going to switch, so it's going to become minus because it was plus here. Sine of the first thing times sine of the second thing. So everybody see that? How we're just substituting the first and then the second. They just happen to be the same. Now, what does that come out to be? Well, I have cosine a times cosine a, which is cosine squared of a. And sine of a minus times sine of a, that's going to be minus sine squared of a. And so we can say that the cosine of 2a is equal to the cosine squared of a minus the sine squared of a. And that is our double angle identity for cosine. Does anybody have any questions about that? Now, the interesting thing, and if you do have a question, please ask anytime. The interesting thing about this is the cosine formula actually has a couple of variations to it. What if both those variations come from the Pythagorean identities, which you can also see on the little sidebar below me. What if I replaced, using the Pythagorean identity, the cosine squared of a with 1 minus the sine squared? Isn't that true? That using the Pythagorean identity, that first line under Pythagorean identity, it says that sine squared plus cosine squared is 1. So therefore, we could write cosine squared as 1 minus sine squared, right? It's possible to rewrite this and say that the cosine of 2a is the same as cosine squared, which is just rewriting as 1 minus sine squared minus sine squared. And look at what we have when we combine like terms. We have 1 negative sine squared, and another negative sine squared makes 1 minus 2 sine squared of a. And that's the cosine of 2a. Okay? So that's another way that we can write. It's an exactly equivalent way, but it's another variation of this that you may see. The cosine of 2a could be written this way, or it could be written this way. Or, of course, there's another one, that's the other 3. We could replace sine squared of a with 1 minus cosine squared, right? Same exact identity, just flipping it around a little bit. We could say that the cosine of 2a is cosine squared a, just like we saw up there, minus, now replacing sine squared a, we can say that that's the same as 1 minus cosine squared. That's our Pythagorean identity, right? Distributing that negative sign and combining like terms, we could say that the cosine of 2a is, we got, looks like cosine, 2 cosine squared a minus 1. Do you see why that's the case? The negative would distribute. You would get negative 1 plus cosine squared a. You'd have cosine squared a plus cosine squared a makes 2 cosine squared a, and then the minus 1's just chilling there. Okay? You may also see that written as negative 1 plus cosine squared, plus 2 cosine squared a. It's the same thing. But that's the third variation of this cosine of 2a formula that we can see. So the cosine double angle identity actually has 3 variations that are all equivalent and all interchangeable, but it's important to recognize those 3 variations in case you see them, because it could just so happen that when doing some problems, this is sort of a preview to proofs, which will come next class, one of these variations will be beneficial versus the others. So it's important to kind of identify which one. Any questions about how we got any of those formulas at all? No questions? Make sense? All right, let's delve into some examples then. Let's delve into some examples. Okay, how about something like this? What if I asked you to simplify an expression like this? I like this one a lot. The cosine squared of 22.5 minus the sine squared of 22.5. I know at least when I first looked at this problem, it should be degrees, by the way. When I first looked at this problem, I was like, how the heck am I supposed to do that? Like, Just seems like the cosine squared of some random number minus the sine squared of some random number. But you might notice here that, ooh, this looks awfully similar to this. Cosine squared of a quantity minus sine squared of that same quantity, right? So we can go backwards from our identities, just like we did with the sum and difference ones, and we could say, well, this is equivalent to this, the cosine of 2a. A here being 22.5, because that's exactly how it matches up here, right? So I can say, well, this is the same as the cosine of 2 times 22.5 by applying our identity. And lucky for us, look at that. 2 times 22.5, that's going to be the cosine of 45 degrees. And what's the cosine of 45 degrees? Of course, it's 2 over 2. Okay. Does that make sense to everybody how that was done? Kind of cool, right? It's just like we saw with the sum and difference. You can go in reverse. Okay? Likewise, you can also expand out. So consider something like this. Let's simplify. Something like 10 times the sine of 75 degrees times the cosine of 75 degrees. How do we simplify something like that? Well, hopefully, after looking at it for maybe a couple seconds, you're thinking to yourself, well, this looks awfully similar to this, right? Sine, cosine, and a number out in front, right? What I would like to see in order to properly use my double angle identity, though, is a 2 here. And unfortunately, I have a 10 here. So how do I deal with that? Well, we do something that's almost a little sneaky. You want to get this to look like this, but currently it's a 10. But you can factor out a factor of 5. Think of if you rewrote this as this. 5 times 2 sine 75 cosine 75. Isn't that the same exact thing? Because 5 times 2 would make 10, and you'd be right back to here. But by writing it this way, it's now a very direct translation from here to here. So we can say that this is all equal to 5 times, the 5 doesn't go anywhere, sine of 2a. A is 75, so we can say it's sine of 2 times 75 degrees. Okay. Well, luckily for us, 2 times 75 degrees is a nice unit circle value. We can say that that's 5 times the sine of 150 degrees. Sine of 150 degrees in the second quadrant, it's the same as the sine of 30 degrees. It's going to be 1/2. So this comes out to be 5 times 1/2, which is 5 halves, or 2.5 if you prefer. Okay. Does anyone have any questions, comments, or concerns about that now? Pretty neat stuff, right? Pretty neat stuff. I think so anyway. I think that's pretty cool. All right, let's take a look at a big problem now. Those are the little simplifying problems. Let's take a look at like a real deal major league problem here. This problem is actually very similar to the ones that you've seen in your previous classes, where it's like, or in the previous pre-calc classes, where we've had to draw a triangle and then say, what's the exact value of all 6 trigonometric functions? Remember that? It was like, oh, theta is between pi over 2 and 3 pi over 2, and the cosine is negative. So you have to figure out, or sorry, it would be like the sine is negative, so you have to figure out that that's quadrant 3, and then draw a triangle and find the other values of the other 6 trigonometric functions: sine, cosine, tangent, secant, cosecant, cotangent. It's a very similar idea here, but instead of trying to find all those things, we're going to draw a triangle and try to find our double angles. So consider a problem like this. Okay? If angle A is acute, meaning it's less than 90 degrees, meaning it's in the first quadrant, right? You could also see that written as A is less than 90 degrees. Okay? And cosine of A is equal to 7 over 25. Let's find the following. Let's find the sine of 2A, the cosine of 2A, and the tangent of 2A. Oh boy. Oh boy. Okay? So consider a problem like that, saying that if angle A is acute and the cosine of A is 7 over 25. Let's find the sine of 2a, cosine of 2a, and tangent of 2a. Well, first things first, let's draw a triangle, just like we saw before. We know that A is in the first quadrant, right? So from the center of our circle, we go up to the first quadrant and construct our first quadrant triangle that looks just like that, right? If A is right here, angle A, the cosine being 7 over 25, how do we define cosine? That's adjacent over hypotenuse. So I would say it's my adjacent side of 7 over my hypotenuse of 25. Maybe you're even thinking to yourself now, well, in order to find sine, which is our very first objective, aren't we going to need the opposite side as well? Because sine is opposite over hypotenuse. And absolutely we do. We need to find that sine. We need to find that side, rather, so we can then find the sine value. So how do we find the missing side of a right triangle? Good old Pythagorean theorem coming through for us. We can say that a squared plus b squared is c squared. 7 squared plus, we'll call this y for now, y squared is equal to 25 squared, right? I believe that comes out to be 49 plus y squared is equal to 25 squared is 625. Subtracting 49 from both sides, I get y squared is equal to something I should be able to do in my head, but for whatever reason right now I'm struggling, 576. And then take the square root of both sides, and you get that y is 24. So it works out to a nice number. Okay? So that was just to find the third side, the missing side of that right triangle. Right? Now that we have that, we could say that the cosine of A is 7 over 25. True, for sure. The sine of A is opposite over hypotenuse. The opposite is 24. The hypotenuse is 25. We can say sine of A is 24 over 25. Right? That's going to help us find sine of 2A, but at least right now we have cosine of A is this. It was given to us, and sine of A is this. Now let's actually work on finding my objectives. We have the sine of 2a. How do we find the sine of 2a? Well, we're just going to use the formula that's right over here. We can say that the sine of 2a is the same as 2 times the sine of a times the cosine of a. So going back over here, I can say that the sine of 2a is the same as 2 times the sine of a times the cosine of a. That's our double angle formula, right? Our double angle identity. We know now the sine of A. The sine of A is 24 over 25. The cosine of A is 7 over 25. So now it's just a matter of inserting or substituting those values and using a calculator. So I can say that the sine of 2A is 2 times the sine of A, which we found, 24 over 25, times the cosine of A. We know that. That was given to us, 7 over 25. And then that just requires a little calculator use. I have our handy-dandy calculator right here. We should be able to plug that in nicely. You don't need a calculator, but it definitely helps. 24 over 25 times 7 over 25, and we should get 0.5376, which if we convert it to a fraction by hitting the math button and go in a fraction, we get 336 over 625. Not the cleanest of fractions, but still a fraction that represents what the sine of 2 times a would be. Okay? The cosine of 2a is found very similarly. I would say, well, what's the cosine of 2a? Going back to our identities, when you're dealing with cosine, you have one of 3 choices. You could use really any of these variations. Personally, I always like to stick with the default variation, just the cosine squared a minus sine squared a. You could certainly use this or this, and you would get the exact same answer, so don't think you're locked into one of the 3 choices. But I'm just going to use the default one to say it's the same as cosine squared of a minus sine squared of a. Well, here's cosine of a, and here's sine of a, so I'm going to say that the cosine of 2a is cosine squared of a. Here's cosine of a squared minus sine of a squared. Just like that. Plug into a calculator, we're going to get, let's see, 7 over 25 squared, squared, minus 24 over 25 squared, and we get negative 0.8432. Converting to a fraction, we get that that's another ugly fraction, but negative 527 over 625. Just like that. And that's the exact value that would represent the cosine of 2 times angle A. I'll give an opportunity for any questions so far. Any questions up to this point? I hope I'm not going too fast. Hopefully I didn't lose anyone. We just get a little confirmation. We're doing A-okay. Feeling great. Alrighty. I take your silence as we're feeling fantastic. Now the big one, right? The scary one, tangent. Oh boy. How the heck do we do the tangent of 2A? We didn't even talk about the tangent double angle formula. So how the heck are we going to find the tangent? Wait a minute. Wait a minute. That's exactly what my mind thought when I first looked at this problem yesterday. I looked at this problem. I was like, well, how am I going to do the tangent of 2A if I don't show them the double angle formula for the tangent, which, by the way, we don't do in CP because it does get pretty messy and complicated. And then I was like, wait a minute. Wait a minute here. The tangent by my quotient identity is just sine over cosine. So doesn't it make sense that the tangent of 2A would be the same as the sine of 2A over the cosine of 2A? And that's absolutely true. That's absolutely true. Okay, if you want to write that in your notes, it might be another good thing to jot down, that the tangent of 2A is sine over cosine. That's our quotient identity. It's right below where my finger's pointing, right there. Okay, so I know the sine of 2A, I just found it. I know the cosine of 2A, I just found it. I can say that the tangent of 2A is the sine of 2A, 336 over 625, divided by the cosine of 2A, negative 527 over 625. And I know that when I write that, I can already see everyone being like, are you serious right now? Look at that fraction. Look at how hideous that is. The tears are already welling up. The tears are already welling up. But we don't panic. How do you divide by a fraction? Very simple. You multiply by the reciprocal. So watch what's going to happen. We're going to do exactly that. We're going to multiply by the reciprocal. We're going to get that this is 336 over 625 times the reciprocal, 625, over negative 527. Hopefully now you see, all right, this wasn't as bad as I thought. 625 over 625 goes away. You're left with negative 336 over 527. And that would be the tangent of 2A. That would be the tangent of 2A. All right. Does that make sense to everybody? How that's done? Something that's kind of cool, something that I'm not going to require you to do, but just as a little quick aside, seeing we have a couple extra minutes here, a little quick aside is you can actually check your work by using a little bit of right triangle trig that we've talked about. Think about it. If the cosine of A is 7 over 25, you could actually find what A is by doing the cosine inverse of both sides, right? Think of if you were solving an equation like we saw with our law of sines and cosines. You came upon something like this, you would do cosine inverse on both sides to get what A actually is, like what actually is angle A. So if you do that, you could say that A is the cosine inverse of 7 over 25, which comes out to be what? Let's find out with our little calculator. The cosine inverse of 7 over 25. We get that it's about approximately 73.7398 if I round, right? We can double that, so let's double it. Because that's 2A, that would now be 2A. That means that 2A would be approximately equal to 147.4796 if I round up, right? And now let's just find out what is the cosine of 2A. So what's the cosine of that result? And we get our negative 0.8432. Converting to a fraction is 527 over 625. Right there, our negative 527 over 625, verified by the calculator, verified by right triangle trig. I'm done. I don't think there's anything else I can do. That's it. I'm going to drop the pen right there. That's a little mic drop for you. Bam. Double checked our answer. We found that it matches up with our right triangle trig. We found that it matches up with our double angle identity. We find that that matches up with our sum identity. It all connects together. Isn't this awesome? This is pre-calc. This is fantastic. I love pre-calc. All right. Well, does anybody have any questions about that? All joking aside, does anybody have any questions about anything we've covered today? All right, just a quick 1 second or 30-second recap. Not 1 second, that'd be really fast. Today, we talked about the double angle identities. I showed you where they all come from. Sine only has one double angle identity associated with it, but cosine has three variations of the same identity. It really does have one identity, but it's presented in three different variations. The sine of 2a is 2 sine a cosine a. The cosine of 2a is cosine squared a minus sine squared a. We can use these double angle identities to simplify expressions like this, noticing that they match up with the identity, and we could replace. We could also notice that this matches up with the identity after a little bit of sneaky factoring work, and we find our exact value there. We can then use them to tackle problems like this, which deals with constructing a triangle, just like we've seen in previous problems in this class. Construct a triangle, use the Pythagorean theorem to find the missing side, and then now that we know cosine and sine, we can plug into our formulas with a little help from the calculator. Tangent looks like this big scary thing. Not scary at all. Tangent we know is just sine divided by cosine. So the tangent of 2a is sine of 2a over cosine of 2a. We found sine of 2a. We found cosine of 2a. Divide them, which means multiply by the reciprocal, and we get our answer. And a little bit of fun checking our work as well. Whew. Any questions, comments, or concerns after that exhilarating pre-calculus experience? It's the best way I can describe it. Well, everyone, if there aren't any questions, that takes us right to the end. There will be some practice problems posted on Classroom. I actually just have to do out the answer key now, and I'm going to do that for you. So I'll do the answer key, make sure it gets uploaded on Classroom along with the practice problems so you can check your work. Please try to do those practice problems in time for next class, which is on Thursday. Again, you'll have the answer key alongside you to check your work. It's not graded, so work at your own pace. Next class, at the end of Thursday's class, we are going to send out just another progress assessment that is expected to be done and returned to me over the weekend. It's the same deal where it's due Sunday night, 11:59 p.m. I'll have that graded. I will post the answer key so you'll be able to see that. And the one that was due this past week as well, I'll make sure I get that to you. Okay? That's it. I hope you all have a fantastic rest of your day. Thank you so much for your attention and focus today, and enjoy the rest of your sunny, looks like outside, sunny Tuesday. Bye, everyone.
Have a nice day, Mr. Giorgio.
Sophia, enjoy the day.